Swayam Prabha. Digital India. Educated India.
Okay, so we talk about inverse, modular inverse on mod operation on ZP. So far we have seen the additive operation on Zn. So let n be an integer. Then we have seen that Zn is basically the residue class. If we take any integer, if we try to divide by n, so remainder will be from 0 to n minus 1. So that class of that class will give us the Zn. So this is basically the which you have seen, this is the residue class or the equivalence class, because this so if A is congruent to B mod n, if A mod n is equal to B mod n. So there belongs to the same class. So this relation we have seen is the equivalence relation, and so this will form this is the a set of integers. So this will form the partition over the integer set, disjoint partition equivalence classes. So this is 0 class, 1 class, dot 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 up to n minus 1 class. So in each class all the elements are under mod operation. So that means if we take element from here, if we divide by n, the remainder is same as if we take any other element, the remainder will be same. So these are all equivalence class. These are for simplicity we write this as this 0 to n minus 1. Then we have seen the operation on this. If we take two element from this Zn, then we have seen how to define. So if we take two element from Zn, then A plus B. So this plus operation we have defined like this, AB mod n. So basically if it is in box form, so box form we are not writing for the simplicity. This is basically AB box of AB mod n. Anyway, for the simplicity we are just not writing in the box form, but this is the way we define the addition. So that means if we take Z, say n is equal to 8. So what is Z8? Z8 basically is 0, 1, 2 up to 7. So that means if we take any integer, if we divide by 8, then the remainder will be from 0 to 7. So now how we define addition? If you take two elements from this, say 5 and say 5 belongs to Z8 and 6 belongs to Z8, so this is AB. So 5 plus 6, which is basically if we do the integer addition, it will give us 11, but 11 mod 8, which is basically 3. Okay, so this we have seen, and under this operation we have seen this Zn is a cyclic group. Is a cyclic group, and 0 is the identity element of that group, and every element has an inverse, and 1 is the generator of this group. 1 can generate the group. Now if n is equal to say n is prime, then say n is equal to 7. So when n is prime, then what is Z7? 0, 1, 2 up to 0, 1, 2, 3, 4, 5, 6. Okay. Then if we take any element A from this, say could be any of these other than 0, 0 cannot generate the group, because if we operate 0 plus 0, it is always give us 0. So if we take any element other than 0, then the group, then if we generate a group by this A, so that means A plus A, that is 2A we define, 3A like this. So this will form a group, and the if we say this is H, so we know the order of the group much divides order of the order of the subgroup must define order of the group, but order of the group is 7. So, 7 is a prime number. So, 7 should not have any factor. So, that means this will be the H should be equal to the whole group Z7. So, that means if it is, if P is prime, then if we consider ZP, then any element other than 0 in ZP minus 0 is a primitive element or is a generator, primitive element in additive sense. So far the operation we have defined the addition. Okay, now we will define the another operation, and modular inverse under additive sense is the inverse. So B will be called inverse of A if B is equal to 0 mod n, then additive sense B is denoted by minus A mod n. So, this is the additive inverse because the operation is addition. Okay. Now, we defined another operation on this set Zn, which is basically multiplication operation. So, again let n be an integer, then we considered the set Zn, which is basically 0, 1, 2 up to n minus 1. Now, we define this operation, multiplicative operation, as follows. If we take two elements from Zn, then we define A cross B is basically A into B mod n. So, in a box form if we write, this is basically A into B mod n. So, this into is basically the real number multiplication. So, for simplicity we will just remove the box. This is basically A into B is basically A into B, the integer multiplication or real number multiplication mod n. So, this is how we define the multiplication. Okay. Now, we can take an example. Suppose n is equal to 8. If n is equal to 8, then what is Zn? Zn is basically 0, 1, 2, 3, 4, 5, 6, 7. So, there are any 8 elements up to 0 to 7. Okay, now, let us define this operation. So, can you please come to the slide? Okay, so, this is the arithmetic operation on multiplication on Z8, elements of Z8. So, the elements of Z8 are written as 0, 1, 2 up to 7. This is A, say, this is B. Now, this is A into B. So, if it is 0, all are 0. If it is 1, so this is A, this is B. If it is 1, so A into B. So, this will all give us 0, 1 like this. 2, 2 into 1 is 2, 2 into 2 is 4. And but 2 into 10, 2 into 8, 2 into 4 is 8, but 8 mod 8 is 0. So, 2 into 5 is basically 10 and 10 mod 8 is 2. So, that is why it is like this. So, similarly we can verify the other. So, suppose A is 4 and B is say 5. So, A into B is basically 20 mod 8. So, 20 mod 8 is basically 4. So, that is why it is 4. So, this is the table where we are performing this multiplication operation on the Z8. Okay. So, now we see whether under this operation we can have a group. So, for group we need to have few properties like closure property, which is quite obvious. If we take any two element from Zn, then A cross B is also belongs to Zn, because we are multiplying and taking the mod. So, it will also belongs to Zn. So, closure property is done, closure is okay. Now, second property is associativity property. So, that means if you take any 3 element A, B, C, this is also can be easily verified. So, this is also okay. This is can be easily verified by the associative property of the real number multiplication. Okay, now the inverse. So, existence of inverse. Do you have any element? So, 1 is the basically serve as the inverse. We called it multiplicative inverse. Multiplicative inverse mod n, because if we take any element A from this Zn, then if we multiply this by 1, so this will give us basically A, which is same as 1 into A, and this is true for all A belongs to Zn. So, this implies multiplicative identity. This is not inverse, multiplicative identity. Sorry, this is multiplicative identity. So, 1 is served as a multiplicative identity of that operator, this under the multiplication operation. So, but inverse, so that means for let A be an element in Zn. So, A then B will be said as the inverse of A. So, if we multiply this, it should give us the identity element under mod n. So, this should give us, so A dot B should be congruent to 1 mod n. Okay. So, then it is called, B is called A inverse mod n. So, if A dot B is congruent to 1 mod n, then B is called A inverse mod n. This is the multiplicative inverse. It may exist, may not exist. If it is exist for all the elements, then we call inverse exist, then it could be a group, because all the other properties are there. And so, AB mod n means, so A into B is congruent to 1 mod n. So, let us look at this table. So, here if we see 1 is served as a identity element, multiplicative identity element, because if you multiply 1 with any other element, it is give us that element. So, 1 into 3 is basically 3, 1 into 5 is basically 5. So, 1 serve as a identity element of this group under the multiplication. But if we take 2 as A, whether 2 has an inverse or not. So, if we have to have an inverse, then there should exist a B here such that 2 into B should give us 1, but there is no 1 exist. So, 2 has no inverse under mod 8, but if you consider 3, then we see here is a 1. So, that means 3 has an inverse. So, that is also 3. So, 3 has an inverse under mod 8, and if you take 4, 4 has no inverse under mod 8. If you take again 5, so 5 has inverse under mod 8, which is again 5. Okay. So, 6 has no inverse, because there is no 1 in this row, but 7 has an inverse, which is 7. So, if A is equal to 7, then B is equal to 7 is the A inverse mod 8. So, for inverse we need to have A into B is congruent to 1 mod 8. So, it is not necessary that every element will have inverse. Okay. So, that is the multiplicative inverse. Now, we define when we say 2 elements are co-prime or relatively prime. This is the definition. definition of co-prime or relatively prime. Okay. Okay, we say two element A B are co-prime. We denote this by this A co-prime to B. This is the notation we can use. If GCD of AB is 1, if the GCD of AB is 1, then we say that AB are co-prime, or in other word AB are relatively prime. So, this is the definition of co-prime. Okay. So, now we will so that means, so suppose we are considering Zn, and we say that if if we take a element A belongs to Zn, and A will have a inverse if there exists a B such that AB is congruent to 1 mod n. Okay. Then we can say that then B is the basically A inverse mod n. Then we can say that A is co-prime with n. So, that means if the GCD of A and n are 1, then only inverse exists, then only A inverse exists, and this is the condition of having the inverse under mod n. So, we take a integer n, we take a another integer, and we say A is having a inverse. This is the definition of inverse, multiplicative inverse under mod n. So, what is the definition? So, you can just write the definition of multiplicative inverse. So, definition of multiplicative inverse. So, let n and A be two integer, then we say A has a inverse. This inverse is basically multiplicative inverse under modulo n if and only if there exists a B such that, so A here ABR belongs to Zn, there exists a B such that AB is congruent to 1 mod n. So, this is multiplicative operation. So, inverse means if we multiply with that inverse element with that original element, we should give the identity element, and 1 is the identity element under the multiplication. So, that means under our multiplication operation it should give us 1 basically. So, this is the modular operation. So, then we say B is the inverse of A. And we will see if A is co-prime with n, then only inverse exists. This theorem will prove in a theorem, if and vice versa. If there exists a inverse, then this will be co-prime. If this, that means GCD of A comma n is 1, then only inverse exists. Then we have a B, then only B exists, otherwise not exist. So, for the existence of the inverse, we need to have this condition. This is the condition, that means A must be co-prime with N. So, if you look at this table here in the slide, so if you look at the table in the slide, so N is here 8. Okay. Now, if you take any element A which is co-prime with N, like 3 is co-prime with N. So, if you look at 3, then 3 has the inverse. Okay. Again, what the element co-prime with? Again 5. 5 is co-prime with 8. So, 5 has the inverse. 7 is co-prime with 8. 7 has the inverse. But any other element like 4 is not co-prime with 8, because GCD of 4 and 8 is not 1. They have a factor other than 1. So, this is the basically having no inverse. So, for the existence of inverse, we need to have A must be GCD of A and N must be 1. So, this we will prove in a theorem which is basically so let us have the theorem. Okay, so this theorem is telling the integer x has an inverse modulo m. Here m is 8, x is say a. If and only if they are relatively prime, GCD of x comma m is 1. So, that means they are relatively prime or they are co-prime. Okay. So, this how to prove this? Okay, suppose x has a inverse. So, it has two part, if part and if and only if part. So, suppose it has a inverse. Suppose x has a inverse. So, x has a inverse means there exists a y, x has a inverse modulo under this modulo m, multiplicative sense. So, that means there exists a y belongs to Zm such that x y is congruent to 1 mod m. Okay. We have to prove that GCD of x and m are 1. So, that means x and m are relatively prime. Okay. So, from here we can write x y minus this is 0 mod m. So, from here we can write m divides x minus x y minus 1. So, that means x y minus 1 should be written as some m into z. So, this implies 1 is equal to x y minus m z. Okay. So, that means any common factor of x and y must divides 1. So, this implies let me erase this. This implies, so we got this 1 is equal to x y minus m z. So, this implies any common factor of x and m must divides 1. So, this implies GCD of x and m must be 1. So, that means x is co-prime with m. This is the one part of the proof. So, if x has a inverse, then it must be co-prime. Now, the other part, if x is co-prime with m, then it has a inverse. So, that part you have to prove now. So, this is the other way around. So, suppose x is co-prime with m. So, that is GCD of x comma m is 1. Now, we have to show that x has a inverse multiplicative inverse mod m. Okay. So, how to show this? So, if the GCD of 1, this we have to, so yeah, so this we will use a theorem which we will prove in the next class, like GCD of any two integer a b can be written as ax plus by, where x and y are two integers. So, this will prove, actually this is basically gives us the extended Euclidean algorithm to find the inverse, but this we have to prove it. So, GCD of any two integer a b should be written as ax plus by form, this linear form. Okay. So, this we have to prove. So, for the time being we are taking this as a theorem, this is a theorem, this we will prove in the next class. So, suppose we take this theorem, then so GCD of this is 1 means, so there must exist a x y such that x is already there. So, there must exist a so GCD of this is 1. So, 1 is equal to some x y plus m z. So, for some integer y and z from that theorem, GCD of a b should be written as ax plus by form. Okay. So, from here what we can say, x y is equal to basically x y is basically congruent to 1 mod m, because if we divide this by mod m, so this is having m, so this part is gone. So, x y is basically congruent to 1 mod m. So, that y is basically inverse of x. Okay. And this y we will find by the by a algorithm which is called extended Euclidean algorithm. So, basically we will try to get this this sum form. So, then this y is basically x inverse, y is basically multiplicative inverse of x. So, the inverse exists if they are relatively prime. Okay. So, it is not that inverse will always exist. So, inverse exists if x is relatively prime with n. Okay. So, now let us talk about what is called, now we will see whether it is from a group. So, let n be an integer Okay. So, now if n is p, n is a prime, suppose n be a prime number, let p be a prime number, prime integer, then we know zp is basically 0, 1, 2, 3 up to p minus 1. Now, if we omit 0, this is basically zp minus 0. So, now if p is a prime, then each of this element is, since p is a prime, then if we take a element from zp star, then a must be relatively prime with p, because p is a prime number. So, p is not having factor other than 1 and p. So, that means if you take any element from here, they are relatively prime with p. So, that means each element here will have a inverse, multiplicative inverse. So, this means zp star, this will form a multiplicative group. I mean basically this is a cyclic group, this is a cyclic group. Okay. So, we are just removing the additive identity element. So, that means this ZP plus dot is a field, and this is a finite field, because number of element is basically this finite set. So, this is a finite field, okay, because this is, we know this with addition there is no issue, because every element has an inverse. With multiplication, so other than 0 element, every element has an inverse, provided P is prime. So, this is a field, this is a finite field, because number of elements are finite. Now, what will be the case if P is not a prime? So, suppose general case, let n be any integer, need not be a prime. Okay, then we define Zn. Then we in our table we have taken n is equal to here, in the slide we have taken n is equal to 8. So, then we have seen all the elements are not having the multiplicative inverse, only those elements who are relatively prime to n. So, that element set we define Zn star. Zn star is basically set of all element less than n such that GCD of a comma n are 1. Okay. Then for n is equal to 8, we have seen the for 3, 5, 7 are the belongs to Zn star. So, this Zn star will form a group under multiplication, is a cyclic group. Okay. So, this is how we define Zn star. Zn star is basically set of all integer less than n, non-zero integer, positive non-zero integer less than n, which are relatively prime with n. So, for each, so in that case, if we define like this, for each of such a, the inverse will exist. So, it will form a multiplicative group, and this is cyclic group. Thank you.